Today we'll learn how engineers design strong, safe buildings and bridges by exploring the forces at play and the materials they use, like steel. Structural design ensures buildings and bridges stay standing by selecting the right size for beams, columns, and other parts to support the structure. When engineers design structures, they think about things like cross-sectional area. This is how big a part looks when you slice it and look at the shape from the side. Next, number of steel bars. If they are using concrete, they also add steel bars inside to make it extra strong. These are called reinforced concrete. Loadings, what force act on buildings. Now let's talk about loadings. These are the forces or weights that push or pull on buildings. Dead load, the weight of the building itself, things like walls, floors, and roof. Life load, the things inside the building like people, furniture, and machines that add weight. Earthquake load, the shaking that happens during an earthquake. Wind load, wind pushing against the building, especially on tall buildings. Rain load, water from heavy rain that can add weight on the roof. Engineers have to think about all these loads when designing buildings to make sure they stay strong no matter what happens.
Building codes, the rules for building safety. To make sure buildings are safe, engineers have to follow special rules called building codes. These codes are made by the government and they help keep everyone safe. Building codes include rules about how strong a building should be, how to keep it safe from fires, how plumbing like water pipes should work, making sure people with disabilities can easily access buildings. Even though building codes don't tell engineers how to design every part, they set standards for safety. Design specifications, guidelines for building strong structures. Engineers use design specifications to ensure each part of the structure, like beams and columns, can support the required loads. Here are some important design specifications. American Institute of Steel Construction, AISC for steel buildings, American Association of State Highway and Transportation Officials, which is AASHTO, for design highway bridges, National Structural Code of the Philippines for building rules in the Philippines, American Railway Engineering, and Maintenance of Way Association, which is AREVA, for railway bridges, American Iron and Steel Institute, AISI, for Old Fort Steel, which we'll talk about later.
Now, let's talk about structural steel. Steel is one of the most important materials engineers use to build things like buildings, bridges, ships, and even cars. Steel is strong due to its iron-carbon mix and high tensile strength, making it ideal for reinforcing concrete and strengthening buildings. Steel's sealed strength is the point where it starts to bend permanently. Engineers design structures to keep loads below this limit to ensure durability. Different types of steel are used depending on how strong they need to be. Plain carbon steel, mostly iron and little carbon, low alloy steel, iron and carbon with some extra metals for added strength. High alloy steel, even more metals are added to special qualities like resisting rust.
Cold form steel is shaped without heat, allowing engineers to bend thin steel sheets into C or Z shapes. This type of steel is used in things like walls and roofs because it's lightweight and still strong.
Welcome to the world of structural design, where every steel beam tells a story of strength and precision. Designing a steel beam starts with understanding the loads it will carry. Engineers must consider live loads, dead loads, and environmental factors. Using advanced software, we analyze these loads. Calculating moments, shear forces, and deflections ensures the beam will perform under real-world conditions.
We begin by inputting parameters, span length, load types, and material properties. This data drives the analysis. Bending moments and shear forces are critical. We analyze these diagrams to determine the beam's response to loads, ensuring safety and stability. Choosing the right beam profile is vital. I-beams, wide flange beams, and channel beams each offer unique strength for specific applications.
Next, we solve for the beam strength using formulas. 1. The moment of inertia as I, and 2. the yield strength of steel as Fy. This helps us ensure the beams can support the intended loads without failure. Safety factors come into play, allowing for unexpected loads. Adhering to public codes ensures our designs meet the regulatory standards. Once designed, the steel beams are fabricated. Precision cutting and welding create the perfect components for assembly. Installation requires teamwork and careful planning. Each beam is positioned with precision to ensure structural integrity.
The result? Structures that not only stand tall but also inspire. Steel beams form the backbone of our modern world. In the hands of skilled engineers and architects, steel beam transforms visions into reality, solving challenges and shaping the future. Join us in celebrating the art and science of steel beam design, where every calculation leads to extraordinary structures.
For problem number 1, determine the plastic section modulus and the shape factor for the given build-up section. For the value of your plastic section modulus, that is equal to Z is equals to A1 Y1 plus A2 Y2. For the value of your C, that is equal to A1 Y1 multiplied by Fy. Next, the value of tension is equals to A2 Y2 multiplied by Fy. Next, we need to find the value of the section modulus. That is Z equals to 120 multiplied by 20 multiplied by 70 plus 20 multiplied by 60 multiplied by 30 and multiplied by 2. So the value of plastic section modulus is equal to 408 times 10 raised to 3 cubic millimeter. Next is the value of shape factor. That is equal to plastic section modulus over elastic section modulus. For S, that is equal to inertia over the value of C. With that, S is equals to 120 multiplied by 160 cube over 12 minus 120 minus 20 multiplied by 120 cube over 2 divided by 8. So the value of S is now equal to 332 times 10 raised to 3 cubic millimeter. For the value of sheet factor, that is equal to 408 times 10 raised to 3 over 332 times 10 raised to 3, and the answer is 1.229.
So for problem number 2, let us consider this asymmetrical beam. So let's compute the plastic moment capacity of the given section with the value of your Fy, which is equal to 248 megapascal. So for this example, we have 350 by 25 in a flange above, and we have a 200 by 25, the flange at the bottom. And we have a web which has a width of 25, or the thickness of the web is equals to 25. And your height is 400. Now, we have to find the area for the value of your plastic moment capacity. So the value of your MP, that is equal to Fy, multiplied by the plastic section modulus. So to find the plastic section model, which is equal to A1Y1 plus A2Y2. So for this one parameter, we need to identify the plastic neutral axis since our section is asymmetrical. So for this example, for us to find that, we need to find the area. The area should be the same from the top of our plastic neutral axis to the bottom of your plastic neutral axis. So for this example, let's assume that the plastic neutral axis is up to here. So our area on top would become 350 by 25, so we have 8,750. That means our area is not balanced, because for sure, our area is bigger at the bottom compared to the top. So let's assume that our plastic neutral axis is somewhere located here on the web. So for that, let's say that this height is equal to y. So let's find the value of y. So from this area on top is equal to the area at the bottom. Let us first solve the one on top. So that is equal to 350 multiplied by 25 plus our base here, which is equal to 25, the height, which is equal to y, is equals to the bottom. So this means that this y is equal to 400 minus y. So for this example, we have a base of 25 multiplied by 400 minus y plus this one at the bottom that has a base of 200, so the height is equals to 25. So the value of your y is now equal to 125 millimeters. So for this example, we can now get the value of z. So let's consider our z at the top. So we have r 350 by 25. So the distance from the neutral axis, we have 125 plus the half of 25 plus this 125 multiplied by the thickness of it, which is 25, multiplied by the centroid from the neutral axis. So we have 125 all over 2. Plus this one at the bottom, so we have the value of 400 minus y, so that is equal to the value 275. So for this example, let us consider this one at the bottom. So we have a thickness of 25 multiplied by 275 over 2, plus the one at the base at the bottom, so we have 200 by 25. Multiplied by, so we have 275 plus the half of 25, so the value of your z is now equal to 3781.25 times 10 raised to 3 cubic millimeter. So we can find the value of plastic moment capacity. So the value of Fy is 248. We will multiply it to Z. So the value of your plastic moment capacity is now equal to 937.75 kilonewton meter. So that's just our analysis in finding the plastic neutral axis.